Okay. So indeed, I'm going to talk about boundary conditions and domain walls in Decomposition mills and the behavior of the duality. This is based on work done in collaboration with Edward Witten, and is contained in these 3 papers. So I'm gonna, this is not time of the talk, I'm gonna go over the basic motivations and just remind you of some definitions of how to define maximal supersymmetric boundary conditions in the Decomposition mills and how to study the properties and duality. Now, we used several different techniques to attack this problem. The use of domain walls and the way domain walls interact with boundary conditions was very useful. So I reviewed that briefly. And I also reviewed brane construction that provides us with a very large set of examples that then we learn how to generalize to situations that where brane constructions were not useful. The zoo of possible boundary conditions for Decomposition mills, even when you require them to preserve as much symmetry as possible, is still very large. It's a very intricate set of possible choices, and the action of its duality in them is pretty beautiful. But for time constraints, I'll mostly give examples that are about boundary conditions in abelian gauge theories, in U1 gauge theories. As you will see, there will be still a lot of interesting physics going on, and it should be enough to give a good feeling of what we can do for the general non-abelian case. So, the motivations for this work, well, the physical motivations were relatively simple. Well, first of all, it's just interesting to study Decomposition mills. At least out of 9 speakers this week, I think. But its duality, somehow, it's still one of the most mysterious aspects of the properties of Decomposition mills. Some progress has been done in the past by studying the behavior of non-local operators, extended operators in theory, like Wilson loops or Duft loops. And there is a feeling that similar insights might be found in studying surface operators or polydimensional 1 operators that have boundaries and domain walls. Now, indeed, we're going to find towards duality there's a lot of very interesting, peculiar concutting dynamics happen near the walls, near the boundaries of Nickel-Fogg gauge theories, or presumably gauge theories in general. Now, another motivation, a little bit more specific, is that we're learning a lot of interesting things about 3-dimensional CFTs. We're finding holographic duals. We're building new ones with Chern-Simons theories. And one very powerful tool to engineer 3-dimensional conforming theories is to start with Decomposition mills. Put it on a segment, if you want. Put boundary conditions at x equal to 0 and x equal to 1. Pick appropriate boundary conditions, pick whatever domain walls you want in the middle, and then flow to the infrared. Similar ideas have been used to understand neuron symmetry in the past. And essentially all the examples of Chern-Simons theories you've heard about this week, for example, can be realized this way. So I think this very large zoo of boundary conditions and domain walls and the rules of how to combine them can provide a general purpose toolset to study 3-dimensional field theories. There was a mathematical application, motivation. Witten has given a connection between a certain mathematical program called the geometric Lagrange program and properties of any Decomposition mills compactified on a Riemann surface. Now, when you put Decomposition mills or a twisted version of it on a Riemann surface, you get some 2-dimensional sigma models with hyperkähler target space. And mathematicians appear to be very interested in properties of D-branes in this sigma model under mirror symmetry, which is a duality of Decomposition mills. Now, of course, if you create a large set of boundary conditions in Decomposition mills, you'll end up with a large set of D-branes in these sigma models. And if you build domain walls, you get line operators, which give you sort of algebras that act on the space of boundary conditions. So until now, these explanations, this interpretation for physics of the geometric Lagrange had produced no results, hadn't gone beyond what was already known by the mathematicians. But these boundary conditions and their properties under duality that we built are pushing through that boundary. So we are providing interpretations for facts that were known but unexplained. So, it seems to be just another here to remind you what an equal Mills is, but at least the matter content of the theory is easy to describe as a dimensional reduction from 10-dimensional supersymmetric Mills. So from the reduction of the 10-dimensional form, you get the form in 4 dimensions, and you get 6 scalar fields with an SO6 asymmetry. The theory is exactly conformal, so there's an exactly marginal governing constant tau. And there is this beautiful superconformal group which combines the conformal group in 3+1 dimensions of the asymmetry together with 32 supercharges. Now we're studying the maximal symmetric super-Mills, and it sort of makes sense to look for maximal supersymmetric boundary conditions first of all. Now, the boundary condition by construction breaks the translation symmetry. Because the commutator of supercharges is a translation, you have to break some supersymmetry when you set the boundary condition. It turns out that you can preserve half of the supersymmetries, 8 out of 16. Moreover, when a boundary condition is, say, x equal to 0, it's natural to still have Lorentz symmetry in the plane of the boundary, and actually also makes sense to conformal transformations in the plane of the boundary. So you can preserve a full 3-dimensional conformal symmetry. And they combine it, so more precisely, there's 3-dimensional superconformal symmetry, which can be embedded in the full symmetry group in a very neat way. And the only reason I'm giving you all this group theory is just to get to this important result, that if you want to get these maximal supersymmetric boundary conditions, you have to preserve an SO3 SO3 subgroup of the SO6 asymmetry. In other terms, out of the 6 scalars, you need to give the same boundary conditions to 3 of them, and other boundary conditions to the other 3. So now let me give you a simple example. Normal boundary conditions. Suppose that you want to give normal boundary conditions to the gauge fields. So you set to 0 the perpendicular component at the boundary. Well, the supersymmetry forces you to give normal boundary conditions to other 3 scalar fields and Dirichlet to the second group of scalar fields. When you have normal boundary conditions, the tangential part of the gauge group at the boundary survives. There is still a gauge theory there, and you can modify these normal boundary conditions by adding matter at the boundary, which is coupled to the gauge fields only there. Another possible modification is to add a Simons coupling just at the boundary. This modification is essentially what you use when you engineer Simons theories. Now, another very basic boundary condition is the Dirichlet boundary condition. You set the tangential part of the gauge field to be 0 at boundary, and again you get 3 of the scalar fields to have Neumann and 3 to have Dirichlet. And in this case, you have no gauge symmetry at the boundary. On the other hand, there is a phenomenon that was very quite unexpected to us. The simplest Dirichlet boundary conditions still have a very large moduli vacuum, moduli space of vacuum. This is because once you break the translation symmetry in the third direction, you are perfectly free to give expectation values to your fields in that direction. Now, typically this will break supersymmetry, but it turns out that if you only turn on these 3 scalar fields and give them expectation values that satisfy the so-called null equations, which are very interesting equations, then you can preserve supersymmetry, and you get a whole moduli space of solutions of these equations, which far away from the boundary look like the original boundary. So they're really a moduli space of possible configurations of the boundary. And once you allow this equation, then you can modify the Dirichlet boundary conditions by allowing the fields to diverge at the boundary in a very precise fashion. Now you could ask me, why do you care about the modifications of Neumann and modifications of Dirichlet? I mean, after all, less. I mean, as duality, the yuan theory is electric-magnetic duality. It exchanges electric and magnetic field. You can define, if all the boundary conditions I define exist for all values of the gauge coupling, so you're perfectly free to make the gauge coupling strong and see what happens. Now in the bulk, you know what happens. If you make the gauge coupling strong, you have a better description in terms of dual degrees of freedoms, which are weakly coupled. Now you can ask, what do these dual degrees of freedom do near the boundary? You're going to find some very interesting answers, I think. So, if this was just a yuan gauge theory, but electromagnetic duality is just electromagnetic duality, you are changing it exchanges the tangential and orthogonal components at the boundary. So essentially, it exchanges normal and direct length. So it would seem that the story is already almost finished. But it turns out that if you look at 1 billion examples, this doesn't work. The zero of the fact is that the northern boundary condition does not have any moduli space. The direct boundary condition does. So they cannot be as dual to each other. So it turns out that the direct boundary condition is dual to the non-boundary condition where you have added some extra degrees of freedom living only at the boundary, which encode this moduli space. Another way to understand it is that if you look at these sort of solutions and you make the gauge coupling, well, there was a gauge coupling hidden here, I didn't write it. So if you make the gauge coupling strong, they get pushed. All the non-trivial part of the solution gets pushed against the boundary. And then, so a strong coupling is really living at the boundary, and again a new interactive conformative theory in the boundary. This is even stranger. The dual boundary condition is a direct boundary condition where you have set up a noun hole, where the scalar fields excess have classical expectation values that are diverging. And the only manual explanation you can give of this fact is that if the normal boundary condition, you have quantum correlation functions of scalar fields with the method of images, quantum mechanically they tend to go towards the boundary. But then somehow, as you go through this duality, they become completely classical expectation values of the fields X. So these facts we essentially found out by engineering the boundary conditions with branes and studying the behavior under duality in string theory. But so this makes clear that there is if you want to study duality and boundary conditions, you have to consider a pretty large class of boundary conditions. And it turns out that all these ingredients can be combined among each other. You can have a boundary condition where you have an ampole, where you put some direct boundary conditions, some normal boundary conditions on different parts of the gauge group, and then you couple a three-dimensional conformal field theory to whatever is left. Now, a way to tame this complexity is to learn how to decompose intricate boundary conditions into simple building blocks. Now, whenever you study the boundary conditions, you can really study domain walls at the same time. When you learned about open strings the first time, you probably remember the doubling trick, in which a boundary condition was studied by reflecting half of the theory on the other side of the boundary. Now you can do the opposite. If you have a domain wall for a theory, you can reflect half of the theory on itself, and you get the boundary condition for the double-dub theory. So in particular, all the analysis I did about supersymmetry on boundary conditions is valid for domain walls as well. And they preserve the same supersymmetry as boundary conditions. In particular, I can play the following game. I can take a boundary at x equal to 0, a domain wall at x equal to 12, and flow to the infrared. This squishes the two together and gives you an action of domain walls of boundary conditions if you want. Now, so you can combine a domain wall and a boundary condition. It is simple, and you might get a complicated boundary condition. Now, following the infrared flow is not always straightforward. You can get pretty intricate things going on, but we sort of built a toolset of simple domain walls and boundary conditions, such that if you open them properly, they flow to the infrared in a simple fashion. and they give you the general boundary condition. So, how do still to understand the basic building blocks, you need some input from outside, and this input from outside, the theory comes from string theory. There are ways to engineer boundary conditions and domain walls from brane systems. This is a very classical system of branes. It's been used in the study of neural symmetry, for example, by Anani and Witte. You take the 3 branes in the 0, 1, 3 direction, the 5 branes 0, 1, 2, 4, 5, 6, and then it's 5 branes in 0, 1, 2, 7, 8, 9. So this system preserves half of the supersymmetries of the D3 branes. If you go to the decoupling limit, the theory of the D3 branes is just an equal UN and equal 4 superior meals. The theory of the 5 branes just decouples because it's irrelevant in the infrared. It's a higher dimensional theory, you don't care about it. But they intersect, see, at a fixed extreme. The intersections are domain walls in the volume theory of the D3 brane. Notice also that this configuration preserves the SO3 cross SO3 symmetry that you wanted to have any chance to get a superconformal boundary condition. And indeed, it turns out that when you float to infrared, all of these configurations give you superconformal boundary conditions. At least you can argue for it using holography, for example, if n is large. Now, as I said, these are the symmetries that are preserved by the brane system before you float to the infrared in the infinite limit. What happens at the intersections? When the D3 brane is intersecting the 5 brane, things are relatively simple. There are some open strings stretched between the D3 brane and the D5 brane. They don't decouple, they live at the intersection. They are actually they form a natural multiplet. And because they are attached to the D3 branes, I'm going to give you an natural multiplet which is charged on the fundamental of the gauge group. So this is just a very simple domain wall where some extra matter lives. If you have an NS5 brane, though, it has a stronger effect on your D3 branes because after all it corresponds to a closed string background with sort of a throat. Well, not quite a throat if you only have a single NS5 brane. But still, several papers in the past have worked out what happens. The NS5 brane effectively splits the D3 brane into 2 pieces. You engage theory of both half spaces and normal boundary conditions at the domain wall. And there are strings stretched between the 2 halves of the D3 branes. So you get bifundamental matter at the boundary. So these two domain walls have been argued in the past to be exactly superconformal domain walls for equal 4 superior meals. Now, domain walls are interesting, but I would like to get some boundary conditions. Now, because NS5 branes split the 3 branes, it's pretty clear that you will be able to just separate the 3 branes on the 2 sides and bring away half of them, so that you have the 3 branes ending on a heavy NS5 brane. And so this allows you to get a boundary condition. They can also break on the 5 brane, although because the 5 brane is much lighter, it gets deformed a lot if a lot of 3 branes handle it. And this deformation is an important effect in field theory. So this way we can engineer boundary conditions for the UN from the Decomposition means. Now, if you have the 3 branes ending on an NS5 brane, this is known to produce a normal boundary condition. And if you have any 3 branes ending on the 5 brane, the system is more complicated because of this deformation of the 5 brane. But things have been worked out a long time ago in the context of studying monopoles. And what happens is that you have the boundary condition modified by the biggest possible noun pole. If you instead get n 3 branes to end on n 5 branes, each D3 brane ending on one D5 brane, you can get the boundary conditions. So we have all the basic ingredients from unitary theories. You can do several games, similar games for orthogonal and symplectic by using Mobier intervals. Anyway, let me give a couple examples in the U1 gauge theory. Well, the first basic example, a D3 brane ending on an S5 gives me Neumann. On the D5 gives me Neumann. The 3 brane ending on NS5. The 3 brane ending on D5 gives me Dirichlet. The triplane ending on NS5 gives me normal. S-duality in string theory exchanges normal and direct, so it exchanges D5 and NS5, and so it exchanges normal and triplet. So this verifies the very obvious fact. And we go to the next example. It's obvious. Consider a triplet that passes through a D5 and ends on an NS5. So here you get an hypermultiplet in the fundamental, which means an hypermultiplet of charge 1. And then you get normal boundary conditions. So this is a way to engineer normal boundary conditions and one hypermultiplet dealing at the boundary. If you do this duality in string theory, you exchange an S5 and D5, you get a D3 that passes through an S5 and ends on a D5. Now you could get the field theory limit of this directly, but there is a better way from Hanani written. You just carry the NS5 across the D5s. There is a brane creation effect, which adds a little fragment of the triplet, which then decombines to the original one. And notice this is essentially the same as this. So the prediction is that this boundary condition is self-dual. Now this already looks pretty fine from the point of view of field theory. I mean, I have a dual gauge theory with electrically charged particles at the boundary. I do electromagnetic duality, which is a purely classical relaxed transformation, and I get magnetically charged particle at the normal boundary. Now, a way to understand this is that it's similar to particle vortex duality in 3 dimensions. So in 3 dimensions, if you have a one gauge theory coupled to electrically charged particles, and you go to the Higgs branch, you can find vortices which carry magnetic flux and are essentially free. Here, you get some sort of vortices with a tail in 4 dimensions, and they don't carry magnetic flux. They are a source for magnetic flux. So they behave like monopoles stuck at the boundary. So when you do, so your S-duality is sort of particle vortex duality happening at the boundary. So it's an example of how even in a very simple theory, S-duality produces interesting dynamics at the boundary. Now this you could have gotten just from field theory, but even the next example in which you have several charge 1 hypermultiplets at the boundary, string theory is already teaching you something quite surprising. So there are some brane manipulations, it doesn't really matter. The point is, so here there were several D5 branes and one NS5 brane. Here several NS5 branes. Between each NS5, I get the gauge theory in a segment, which in field theory limit in the infrared is going to give me some 3-dimensional gauge theories, all living at the boundary. There are hypermultiplets charged on pairs of these gauge theories that live across the NS5 branes, from open strings across the NS5 brane. And there is a final hypermultiplet which is charged both to one of these U1 theories on the boundary and to the bulk U1 theory. So as you go to the infrared, you're getting a sort of intricate field theory living at the boundary and coupled to normal boundary conditions. So this, I represented this field theory with quiver. So there is a bunch of U1 gauge theories by fundamental matter and a pair of fundamentals. Now, something that can help you understand what's going on is that this field theory has a very simple mirror, meaning that if you go to the infrared, this becomes a complicated superconformal field theory, which is dual to a superconformal field theory, which is just a single U1 gauge theory with n coupled to n charge 1 hypermultiplets. So this sounds suspiciously similar to what we had in the original boundary condition. So we started with a situation where a bulk U1 gauge theory was coupled to n hypermultiplets. And now you get a situation where the bulk dual U1 gauge theory is coupled in a funny way to a 3-dimensional field theory, where 3-dimensional U1 is coupled to the same matter. And indeed, this is very easy. This sort of idea. Okay, so this is in general how you get boundary conditions. You engineer these dual boundary conditions. You engineer them with branes. You do a duality in the brane system, and you move around the branes to get something that's simple to interpret, and you read the result. And so you can get a prescription, I was saying, on how to go from a boundary condition for a Yuan gauge theory to another boundary condition, you couple suppose you had a boundary condition where you have Neumann and a coupling to a three-dimensional CFT. Well, you should just couple the three-dimensional CFT to a three-dimensional Yuan theory. This produces a new three-dimensional theory. And in the infrared, a new CFT. This CFT is what gives at the boundary of the dual boundary condition. So this S operation actually has been introduced for Yuan some time ago by Witte, and S squares 1 as it should. And you can also even define a T operation where you add a Chern-Simons coupling at the boundary, and then SD cubed can be shown to be 1. So you get the full SL2Z action of duality group on boundary conditions for the Yuan gauge theory. Now, can we prove this? Yes, there is something called the engaging trick. Essentially, it's if you want to, suppose that I gave you the dual boundary condition and you wanted to read what CFT lives there, well, you would like to remove the coupling to the bulk theory. The way you remove the coupling is just by putting a Dirichlet boundary condition at some distance and flow into an infrared. This kills the bulk theory. Now, suppose that I go as duality to this configuration. I go to configuration where here I have the original boundary condition, not the dual one, clearly. But here I have the dual Dirichlet boundary conditions. And I have non-boundary conditions on both sides, so I get so in the Yuan case, this is just Neumann, so I get the Yuan gauge theory coupled to the original CFT. But this prescription clearly is going to work for any gauge group, every non-abelian gauge group, as long as you understand what lives at this dual of a Dirichlet boundary condition. The CFT TG is a key actor in our work and has a lot of interesting properties. So as long as you can do as dual for a Dirichlet boundary condition, you essentially have a prescription to do as dual to any boundary condition. Okay, so where can we go from here? As I said, you can use this tool set as a way to engineer interesting three-dimensional conformal field theories and study them. And there might be new sort of symmetries that are valid for situations with Chern-Simons couplings. I think that something very interesting to do would be to look at the holographic dual of these boundary conditions. I mean, there is some tension in there because we can produce such an immense set of boundary conditions. Right? You can put a domain wall where some matter which lives in the 57th symmetric product of a fundamental is. Is this going to still have an holographic dual, or is it just going to break almost the ADS-CFT correspondence, break the planar limit? I think it's also interesting to try to generalize what to do to situations with less symmetry. Those NAM equations some time ago, slides ago, here, generalize immediately to N=1 gauge theories with matter. And you might wonder, is there some sort of analog of the non-pole boundary conditions for N=1 gauge theories or N=2 gauge theories? And can we learn something from them? Can we do anything useful from them? I mean, besides the obvious idea of trying to see what happens to them under such dualities, or dualities in the theory, I think that it's just interesting to study a large set of boundary conditions of a given theory.